Power delivered to the battery. We know the voltage across the battery.
I just got
Turn on. Oh, great.
Oh no. Okay. See, Rachel, what you do?
Okay, so we know that. So we know the voltage across the battery. So all we need is the resistance of this metal bar thing. And once we find that resistance, then we will be good. So the resistance, of course, is just going to be rho L over A. They give us the resistivity here, which is the rho. They give us the cross-sectional area here, and they give us the length there. So then I just use P is equal to V squared over R. So then that becomes what? V squared A over rho L. And that will give that out. Yeah. Resistivity is a function of a material. Resistance is a function of an object. Exactly. The lowest resistivity, it's a rating of how difficult it is for charges to pass through you. So, like, I think silver is actually the best conductor because it's the lowest resistivity. Yes, exactly. I mean, you could. I just choose to use this because that's direct and I'm done. But if you wanted, you could use P equals IV, then use V equals IR to calculate I, and then plug it in if you want. That's fine. Those are reasonable choices. All right. Then on the diagram below, indicate the direction of the electric field in the bar. Okay, so if we just look at this and say, okay, which way does current flow? Conventional current. Conventional current goes like this, right? So then which way must the electrical field flow? Just so we can see here, this is their solution, V squared over R. They just calculated R, boom, got that done, 11. This is what you were talking about, Jonathan. They calculated I. Once they calculated I, then they plugged it in. Same smell. This is that thing where conventional current flows from A to B, and then if conventional current is the movement of positive charges, then the electric field must go that way. Yes? It doesn't matter. The electrons go the other way, right? Like if we go back to here, they tell you electrons are the sole charge carriers in the bar. Isn't that true anyways? Right? Remember we said conventional current is sort of this thing that just exists as a convention. It's not real. There are no movement of positive charges in the circuit. It's the electrons. Well, you know what? Let's answer this question with electrons. Okay? Electrons move this way, right? Which means the field must point which way? It must point this way. Because electrons go against the direction of the electric field. Positive charges go with the flow, remember? Electrons go against the flow. Okay, they're the grumpy, whatever charge that doesn't like to do anything the right way.
Wait, so basically in explanation, like, you say that the negative electrons go against the field?
Yeah. Like, what, okay, I would say, the easiest answer, frankly, is just to say conventional current flows from the plus to the minus. And that means from A to B. Therefore, the electric field goes from A to B. Because if positive charges are going from A to B. So you could also say electron current goes from the negative to the plus. And if electrons are flowing from B to A, since electrons go against the flow of the electric field must go from A to B. However you want to do that. Okay? Then calculate the strength of the electric field in the bar. Okay, so then it's a function of just doing a little bit of math. We know that the voltage across that resisting unit, that little bar, is 9. Right? We know the length, so we can get the volts per meter and get the electric field. Right? Because there are two sets of units that give us the strength of the electric field, volts per meter and newtons per coulomb. Remember this? The force of an electric field is EQ. So E is F over Q. Or you can just say the strength of an electric field is defined by this.
Really? Is that simple?
Yep. So that's newtons per coulomb. Okay. Then they use some crazy current density thing, whatever. That looks annoying, so I don't want to do it. Just so to kind of review, current density is just the current per area. So by taking the current density and multiplying it, interesting, by the resistivity. Oh, this is like a slick units sort of thing, right? This is actually pretty clever by units because if you look at these units, when you multiply, you're going to get ohms, amps per meter, which is like a pretty weird thing. But then when we look at like V equals IR, right? That's amp ohms. So by looking at the resistivity and seeing the units of resistivity as ohms per meter, this person realized, oh, if I multiply ohms per meter times amps per meter squared, I will get the right units. I'm guessing not a lot of people get this. Yeah.
So basically for the first one, it just says that E equals all voltage divided by the weight of the bar, and then
That's it. Just divide it. But the concept also is important. Get the concept, not the math. The math is obvious. The concept is, what are the units of electric field strength? There are two choices. Newtons per coulomb or volts per meter. And if you look at this circuit, do we not know the voltage across this thing? Yeah, we know it's 9. And because we know the length, that should click to us and say, oh, volts per meter. Done. Yes? Does that make sense?
can they change it if you don't get the scientific notation?
Well, I mean, no one's going to care if you use, there is no, like, it's not like they're going to say, oh, you know, you used incorrect. It's not like light, if you pick like, I don't know, red light, which is like 700 nanometer wavelength. If you say 700 times 10 to the minus 9, or if you say 7 times 10 to the minus 7, you're not going to get dinged on an AP test if it's the same number. Now, if you forget the units, that is going to ding, you are going to get dinged. They'll come back and subtract the point from those units. Okay, we move on. Calculate, okay, so in this one, there's a magnetic field into the bar is added to the region. So that field is going in like this. Right-hand rule, all that stuff. Calculate the magnetic force on the bar. It's pretty straightforward, right? BIL, we're done. So for B, F is BIL. Magnetic field strength times current times length. Boom, 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 done. Questions? Yeah. What do you what? Do you know the resistance? Yes. That was rho L over A. Yeah. Since you know the resistance and the voltage, ding, just start it.
Wait,
Good.
so we know what the resistance is because of the resistivity given to us in the problem, and then how do you find it? How do you find it? How do you
Resistance, R is rho L over A. Remember we did that back up here. Up here. R is rho L over A. So the resistance is 7.2 ohms. So the best thing that you could be doing on your paper is writing word notes, right? Because this is already online, so don't copy this. That's like wasting your time. What you should do is jotting down notes, like, oh, think about resistivity, or don't forget this. I don't know, buy a dozen eggs on the way home, whatever. But write down notes on here that clarify this. Don't copy this because it's already online. Okay.
So basically, resistivity is Y or whatever that, and then like
It's rho, yeah.
rho, and then resistance is actually R.
Yeah. Well, yeah, and the relationship is that resistivity is inside of resistance. All right, so calculate the magnetic force on the bar. We did that already. Then, the electrons moving through the bar are initially deflected by the external magnetic field. On the diagram below, indicate the direction of the additional electric field that's created in the bar by the deflected electrons. So if the electrons get deflected, well, oh, sorry, I guess I should show you here first. If the electrons, the electrons are going from B to A. Does everybody pull that? So then, using the, right, they get pushed up to the top, right? Does that make sense? So when the electrons go through here, they're going to be up here. Well, then what's the electric field going to do? The electric field is going to go like this. Yeah, just. Yes. You don't really use. Yeah, for part B, there's no magnetic field yet, so you don't use any hand rule. There is no hand rule. Does that make sense? Yeah, the X is going in. Okay, electrons go from B to A, so I point my thumb towards A, and means the electrons get pushed out. Sure, I could use the right hand rule too if I wanted, right? That's a magnetic field. Right. The one that's the field that's up there, the X's, that's a magnetic field. You realize that, right? So what they're trying to say is when the current, so if you take this thing and it's just going, right? The circuit is going. We know the electrons are going that way, B to A. Now we take this thing and stick it into a magnetic field. What's going to happen is the current that's moving is going to get deflected by the magnetic field. Does that make sense? Yeah. Okay. And they get deflected, the electron current gets deflected upward. Does that make sense? That's exactly it. It's just being forced upward. Because there's more electrons on the top of that block than there is on the bottom of the block, that means there's now going to be an electric field caused by that separation. Because remember, you take a neutral charge, you pull apart plus and a minus, electric field. Right away. Boom. Boom. Between it. So anytime you do a charge separation, bam. Okay, anytime you get a dipole moment with that, boom, you get that moment is the electric field. Right? And if you want to think about it this way, the regular positive current goes one direction, electron current goes the other, the positives get pushed to the bottom, the negatives get pushed to the top, so when you draw the pluses and the minuses up here, the electric field falls from that. Yeah, because there are no protons in the circuit. Because remember, we use that conventional current. All right, any questions on that? Question? Good discussion. Yes.
So how do you figure out what direction is the electric field from?
Because if there's electrons at the top, show me an electron with your hand. What does the field look like around an electron? Yeah, like this. See, the arrows are pointing towards the electrons. Well, if the electrons are up there, the field must be pointing up.
The field is going up?
It must be pointing at the electrons, right? Now, you could say that there's also a field out here going like this, but that's not what it asked. It asked for the the electric field created in the bar. So I don't care about those. That's why I only draw it inside one.
Oh.
Okay?
And then like when you're using the right hand rule or the so-called right hand rule.
Yes, exactly.
A few is only 18 feet, not out of feet.
Yeah, because your fingers are in. Yeah. Okay, questions? Okay. The last thing is the electrons eventually experience no deflection and move through the bar at an average speed of this. Calculate the strength of the additional electric field indicated in part E. So if they experience no deflection, that means the electric field matched up with the push of the magnetic field. So we're just saying Fe equals Fb. Standard sum of the forces, and because I'm lazy, I don't write it. Ding. F equals FB, QEQ is QVB, so E is VB. Yeah. F equals ILB. Well, you could. Yeah, like you just have to. You don't know. Like if you look at Q and V, what does that come out to be? Because V, like Q is in coulombs, right? And then V is in meters per second. So then a coulomb meter per second, like coulombs per second is I, right? And then, okay, clearly I'm not communicating this well, so I'm just going to write it because it's easier. Okay, take a look. QV, right, equals coulombs times meters per second, yes? What is a coulomb per second times a meter? That's IL.
Really?
It's like the same thing. So, yes, you can use VIL. You just have to unpack it so that you can answer the key. Okay, any other questions? That makes sense. Everyone good?
V being velocity, right?
V being for this?
Yeah.
Yeah.
Why would there normally be deflection though? Or like
Because what they're saying is like the magnet okay go back to the problem so you can see it. So we said the conventional current was here, so this is being pushed up because the electric field goes up. As the electric field gets stronger, here we go. Think of it like this. We said there's a bunch of electrons getting pushed up here, right?
Yeah.
Now, if there's electrons getting pushed up there, as new electrons come in, where are they going to get pushed by these? Yes, they're actually going to get pushed down until you have an equilibrium state where the electrons flow straight across the middle. And that equilibrium state is a function of a balance between the magnetic strength and the electric strength.
So basically it's just because like electrons always deflect like similar electrons.
Well, it's not always. It's that when the electrons were flowing fine,
Yeah.
when we put it in the magnetic field, the electrons got shoved up to the top. Once they got shoved up to the top and they started collecting up there, or like getting too much up there, then that electric field, like they started pushing new ones down. And then it finds some equilibrium where the new ones, that even newer ones, just go straight across.
Okay, so it's basically equilibrium. That's because the E feels fine with the
Yes, exactly. Okay. Any other questions? Already.